talked about gravity in the context of things hanging out near the Earth's surface, but in this unit we're going to be dealing primarily with orbits and stuff like that, planets and stars and whatever else. So when we get far away from Earth's surface, then we cannot just use mg for gravitational force. We need to use the full form of Newton's law of universal gravitation. What does the word universal mean? Or every one, or every whatever. In the case of the law of gravitation, it means that this is a description of the force that exists between every pair of particles in the universe. Generally, there are only a couple things that have a non-negligible gravitational effect, like as we are sitting on Earth's surface, we don't need to be concerned particularly with the gravitational force the moon exerts on our bodies, because Earth's pull is so much stronger. But every particle in the universe does exert a gravitational force on every other particle in the universe, but many of those forces happen to be negligible. So the law of gravitation, this constant, capital G, Newton didn't know what G was. What Newton said is that the gravitational force between two particles is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So he said some constant times m1, m2 over r squared. This Ng is a constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared are its units. Like many of the fundamental constants of the universe have weird units. It would be a good idea right now, pull out your calculator, and it'll make your life easier for the rest of this unit, 6.67 times 10 to the minus 11th, and store that as G. And then you can just type G anytime you want to do a calculation with the law of gravitation. Bless you. I think if you're on the 89, it'll have to be a lowercase g. You can probably make a capital G somehow, but I'm not entirely sure how. As you already know, the gravitational force is attractive. It pulls objects toward each other. So that's how you figure out the direction of the gravitational force on a given object. And I think I mentioned this last semester, but the other class didn't remember, so maybe I'll say it again. Or maybe I didn't say it. Maybe I'm just reminding you. But according to Newton's law of universal gravitation, we do all exert a force on each other as well. So whatever anyone may tell you, you are, in fact, attractive. Unfortunately, you must also be aware that your attractiveness is negligible. Which is why we don't go like, and yeah, when you're walking next to each other and run into each other, that's a psychological thing, or you can't walk straight. It's not the gravitational force, because it's way, way smaller than even the frictional force between your feet and the floor. Actually, we multiply this out, take G times, I'm about 85 kilos. David, what's your mass?
77.
It doesn't matter if you're exactly accurate. What are we, about a meter apart?
Yeah.
So the force we exert on each other is on the order of 10 to the minus 7th newtons, while the gravitational force the Earth exerts on me is 833 newtons. So that's about 9 orders of magnitude larger. So that's why we don't care about the gravitational force we exert on each other. The law of gravitation also corresponds with Newton's third law, which is good, because if Newton had published laws that conflicted with each other, then people probably wouldn't have taken him very seriously. Because, if you flip the two masses, if you take Earth's mass, my mass, or then you go my mass, Earth's mass, they're just multiplied together, so you get the same thing, which corresponds to Newton's third law, which says that gravitational force the Earth exerts on me is the same as the gravitational force I exert on the Earth. Yeah. And the other thing I want to mention here is just this G and just how gravitation works in general, along with a lot of other things, are part of what is known as the fine-tuning argument, that the way that these laws function and the values of these particular constants are what have made it possible for life on Earth to exist as it is. That if G had been somewhat different, maybe Earth would be in a closer orbit and would be too hot to live on, or like it might be far. If it was smaller, it might be farther away. Actually, if it was bigger, Jupiter might have taken it more mass and become a star. So, like, you know, the physical laws are set up in such a way that life, human beings, and the life on this planet are able to exist, and there are so many of those things that have to line up just right and do line up just right for us to exist. So, you know, this is part of, I would say, a reasonable argument that there is some kind of creator, and that this didn't all come together by chance. I would echo the quote by I forget who said, "I do not have enough faith to be an atheist," because it seems much more probable that there was a logical mind behind the creation of this than it all came about by chance. So it takes a lot of faith to be an atheist, I think. Right. Anyway, so let's do some calculations. We've got 3 asteroids momentarily situated in a line. We're assuming, for the sake of this problem, that they're far away from other stuff, meaning that any forces from other objects are negligible. So we've got A, B, C. They're situated. We've got A chilling out here, and B 1.1 kilometers away, and then C 4.3 kilometers away. So if we want to find the net force on A, what forces would contribute to that? I'm sorry, say it again.
The gravitational force would be on A and force on C.
Right, B on A and C on A. And what direction is the force of B on A? Is negative a direction?
Left.
Right, left, up, down? To the left?
B on A. Right.
The force on A is to the right, because it's going to get pulled toward B. The force is attractive. So and then what about from C on A? Also to the right, because A is being pulled toward C. So we need the force from B and the force from C. So for the force on A from B, we can start punching stuff in. Alberto, what should I multiply out? We got G times, which is
3.8 times 10 to the 5th times 5.6 times 10 to the 6th.
over
Divided by 1.1 squared. No. Kilometer squared.
G has units of meters, which means we need to be in units of meters. Okay, so we can get a number for that. Another little calculator trick that makes it a little bit easier to punch things in. So when I do this, I G times, and then I move my powers of 10 to the back. 3.8 times 5.6, and then we've got a 5 and a 6, so that's times 10 to the 11th.
Where'd you get the E?
Right here. I don't know where it is on the 89. The E means times 10 to the whatever.
Okay, nice.
Yeah. So it's small, fairly small. And I'll store that as A because we'll also need it to find the force on B later on. Then we've got the force AC. Yoonjung, what would that be?
3.8 times 10 to the 5 times 8.7 times 10 to the 5 over 4,300 squared.
Indeed. Punch that in. This is 10 to the 10 powers of 10. Comes out to 1.19 times 10 to the minus 6th. As I speak, I will store that as B just because. And then to get the answer to part A, what do we do with those, Andrew?
I just add them.
You just add them because they're in the same direction. And we get about 1.185 times 10 to the minus 4th newtons. Pretty small. As a point of reference, Earth's mass is something times 10 to the 24th, I believe. So, these are like, you know, well, it would take many of these asteroids to make an Earth. Like 10 trillion-ish? Is that right? Trillion is 10 to the 12th. No, it's more than that. Quintillion, I think. Anyway, whatever. Whatever 10 to the 18th is. All right. If we want to find the net force on B, what else do we need, David?
We need C and B.
Right? Which would be what?
Massive B. 5.6 times 10 to the 6 times 8.7 times 10 to the 5th over 3.2 squared. 3,200 squared.
Righto. 3.17-ish times 10 to the minus 5th. Store that as C. And then, what do we need to do, Taehan? What do we need to put together? Finding that force on B.
And then we need to find force on A on B.
Mm-hmm.
So it'd be G times. It'd be the same.
Which we already did, right? So what signs should we give those?
B, C on B should be positive, and then A on B should be negative.
Right, because the force from C is to the right, the force from A is to the left. So we subtract those two. And we get, well actually, technically for A, I should have said in the plus X direction. Because the question doesn't say magnitude. So then this is about 8.557 times 10 to the minus 5th newtons in the negative X direction. And then for C, we would need these two. Both of them are to the left. So we can take, as I have labeled them, negative B minus C. And I'm not going to, you can punch that in if you want to, I guess.